Algebra 2 students, today we are going to talk about the characteristics of polynomial functions. We have actually already been working with polynomial functions because one type of polynomial function is a quadratic function, but we're going to learn about some other types of polynomial functions as well. This is an example of a polynomial function right here. You've got 1, 2, 3, 4 terms in this one. Polynomial functions mean many terms. So they could have 4 terms, or they could have 3, 2, or 1 terms, or they could have like 50 terms. I'm going to give you an equation for a standard form of a polynomial function, but I find that the variables make it seem more confusing than it is. So really here, this example is the best thing to consider when you're thinking about a polynomial function. But here's your standard form. You've got your first coefficient, your leading coefficient, which we're going to call a sub n, and then you have x to some power. Your next term has a coefficient as well, a sub n minus 1, and your x is going to be raised to the n minus 1 power. So in standard form, you have your biggest exponent and then your next biggest exponent. And then you're going to have your next, which means it's going to be 2 less than the first one, x raised to the n minus 2. So your exponents keep getting smaller until you get down to the constant term, which does not have an x on it, and we would just call it a sub 0. Constant term does not have an x. Here are some rules for polynomials. So I'll write that right here. First two are rules to be a polynomial. Your coefficients, the numbers in front of the x, those need to be real numbers, so no i's. The exponents have to be whole numbers, which means they can't be negative and they can't be fractions. So my exponents are 3, 2, and 1. They're all positive. None of those exponents are fractions. The degree of the polynomial is the highest exponent. So looking at this polynomial, think to yourself, what would be the degree, the highest exponent? And hopefully you said 3. 3 is the biggest exponent, so 3 is the degree. The leading coefficient is the coefficient of the term with the highest exponent. So looking at this term with the highest exponent, this is also called the leading term. You're thinking, what is the coefficient? What number is being multiplied times my x to the third? So you probably noticed the negative there, but we don't see a number. Remember, that's going to be the same as negative 1. So my leading coefficient is negative 1. My leading term is negative 1x to the 3. The constant is the y value of the y-intercept, and the constant is the term with no x. All right, so think to yourself, what would be the constant in this polynomial? And hopefully you said 17. All right, we're going to do some examples of polynomials. And these examples all have names that depend on their degree. So when the degree is 0, meaning you don't have any x's, we have a constant function. An example of a constant function might be y equals 3. So that means all the y's are 3, and it looks like a horizontal line because all of the points on this line have a y of 3. A linear function is when the degree is 1. So the highest exponent you have is just x to the 1, and a very simple example is y equals x. Remember, y equals x means x to the 1. And that's going to look like a line here. Okay, a simple quadratic function is just y equals x squared. So because of that too, your degree is 2. And remember, that looks like a parabola shape. And similarly, a very easy cubic equation is y equals x to the 3. Now, we're starting to get to some types of functions that will have different shapes. it is possible to look like the shape y equals x to the 3, which is like this, or it might actually look different. It might be something that's like this, okay? So you can have different shapes for these higher level ones, but if it's a cubic function, the degree is 3. Okay, remember that these will have arrows that make them go on forever. An example of a quartic function, and this is one that you can graph in Desmos so you can see its shape more precisely, might be y equals x to the 4 plus 2x to the 3 minus x, and that one is going to look a little bit like a W shape. So it'll be like that. So graph that in Desmos. You should see it look like a W shape. And to get a quintic, you're going to need to have a 5th degree. So let's go back. This was degree is 4, and quintic is when your degree is 5. And one example is y equals x to the 5 minus 5x to the 3 plus 4x. And that one is going to look a little bit different. It's going to look a little something like that. All right, down here, I'm going to have you decide whether you think these are polynomials. So this would be a good time to listen to the instructions and then pause the video. So you're going to decide if it's a polynomial by deciding if it follows these rules up here. Do they have coefficients that are real numbers, and are the exponents whole numbers, not negative and not fractions? So pause the video, write yes or no for each one, and if it's yes, put it in standard form and say the degree and the type. All right, in the first one, I hope you noticed this negative exponent and you wrote no. For the second one, the coefficients are all real. It's fine to have a 1.5 for your coefficient. The exponents are all whole numbers, so that's fine too. So we're going to put yes for number 2. And to put it in standard form, you need to put the term with the biggest exponent first, then the next biggest exponent. We don't have any x squared, so we'll move on to 4x, and your constant term is the last one. Because the degree is 4, that makes it a quartic equation. And let's look at the next one. Number 3. Number 3, your coefficients are all real. It's okay that this is a root 2. That is real. And your exponents are all whole numbers. So this is a yes. To put it in standard form, we would have the one with x to the 5th first, then the term with x to the 4th, then the term with the x, and then the 1. Because the degree is 5, you should have written quintic. And the last one, you noticed that there was a problem here with the x. So your exponent can't be x, it has to be a whole number, so we're going to say no. All right, moving on. Over here we have something called the fundamental theorem of algebra. It's very wordy, but we're going to write it in shorthand right here. If a polynomial of degree n greater than 1 and the polynomial equals 0 has exactly n roots, including multiple and non-real roots. Roots are called zeros, and they're also solutions to the equation p of x equals 0. We can find the real roots on the graph as x-intercepts, so any real roots will be there as x-intercepts. Non-real roots come in pairs, and we don't see them on the graph. So the important thing to remember here is that degree of your polynomial is equal to the total number of roots. All right, so a polynomial of degree n is going to have up to n minus 1 turning points. So if you can count the turning points, then the degree might be 1 bigger than those turning points. For example, looking down here, I have 1, 2, 3 turning points, and that would make the degree 1 more, so that would make the degree 4. Here, the example says if you have a degree 3, you're going to have 3 total roots, and at most, maybe not exactly, 2 turning points. So going back to our example here, we had 3 turning points, 1, 2, 3, and so that means the degree might be 1 more than that, 4, which would make it a quartic. The domain is the x values. Even though this side keeps going up, it also keeps going to the left. So we're going to start our domain at negative infinity. And on this side, it's going up, but it's also going to the right to positive infinity. Every polynomial has the domain negative infinity to infinity. The range starts at my lowest value here, which looks to be negative 6, and it ends all the way up here at positive infinity. Because the degree is 4, we have 4 total roots. When I look on the graph, I see 1, 2, 3, 4, so 4 real roots, which means 4 total, and 4 of them are real. I have 0 non-real roots. Reading on the graph, it looks like my zeros, or my roots, the x-intercepts, are negative 4, negative 2, negative 1, and 3. For increasing and decreasing intervals, my increasing intervals are going up as I read it from left to right, so here to here, and then here to here. Remember that you're looking at the x value, so it looks like I start increasing at negative 3.5, and I continue increasing till the very top here at negative 1.5. Then here at positive 1.5, I start increasing again, and I keep increasing all the way over here to positive infinity. Decreasing intervals, this one is decreasing, and this one, okay? So, decreasing from negative infinity until here, which was negative 3.5, and I'm decreasing here as well from negative 1.5 to positive 1.5. My end behavior is asking what happens on the right of the graph and what happens on the left of the graph. So on the right, as x goes to positive infinity, my y, or my f of x, is also going to positive infinity. On the left, as x goes to negative infinity, my y, which is my f of x, is also going to positive infinity. So I'm going to leave this one for you to work on, give that a try, and then you'll be able to check it against a key that will be posted in Schoology.